Okay, in this section, we're going to learn another way to take limits. So typically when we have taken limits, we do a substitution to start, and if we get to a number, we're done. But when we end up with a 0 over 0 or infinity over infinity, that's what are called indeterminate forms, and that's when we have to do something else, like maybe look at the graph or factor, things like that. So if you look at all the first 6 problems on this page, all of these, if you try to do a direct substitution, ends up with either 0 over 0 or infinity over infinity. So if you look at this first problem right here, if you just plug in infinity, 3 times infinity is infinity, 4 to the infinity is infinity. So this is going to be an indeterminate form. But the way we can think about this is we can just think about this intuitively a little bit. You have a linear function in the top, 3x, but the bottom is an exponential function, 4 to the x. So if you think about it, the exponential function on the bottom grows at a much quicker rate than a linear function on the top. So in a fraction, if the bottom of the fraction gets bigger and bigger much quicker, the whole entire fraction gets smaller and smaller. So this is really 0. So we're just kind of doing this intuitively. If you look at the graph of this in the calculator, you will notice this graph approaches 0. In the same way, number 2. You have just 3 on the top, which is a constant. You have an exponential on the bottom, and we are making x infinitely bigger. Again, the bottom of the fraction gets bigger and bigger, so the whole entire fraction gets smaller and smaller until it reaches 0, or it approaches 0. Now, on the next one, it's flipped. You have the exponential on the top, and you have an x squared on the bottom. In the long run, the exponential always outpaces any type of polynomial, even if this was to the 200th power. In the beginning, the x to the 200 may be bigger, but as x gets infinitely bigger, the exponential always grows at a much quicker rate. So in this case, since the exponential is on the top of the fraction grows faster, much quicker, so the entire fraction will just get bigger and bigger, so this limit is actually infinity. Now, if we look at the next 3, these are problems that we've done before. So if I go to infinity on number 4, you will end up with infinity over infinity again. But in this one, both of them are polynomials. So remember, we did problems when you have things raised to the same power. We look at the ratio of the lead coefficients. Really, this one becomes very important in the long run. So this limit is 1/3. And then I'm going to jump down to number 6 first. Remember, we also talked about if the bottom of the fraction is a higher degree then, if you just have polynomials on the top and the bottom again grows much quicker, so this is going to approach 0. Number 5, if you just plug in 3, you get 0 over 0, again, which is indeterminate, but this is the type of problem where we did this by factoring. So if I factor this, notice those factors will cancel, and if I plug in the 3 now, I get to 6. So these problems here are either problems that we can do a little bit intuitively, or we've learned how to do these before. Now, there are going to be problems on the bottom part where you still get 0 over 0 or infinity, but we're not going to be able to use the methods that we used above. So we're going to use something called L'Hopital's rule. And that's basically any way to work with limits where if you try to do a direct substitution, you get 0 over 0 or infinity over infinity. This is the key. You need to check that this happens, and then you can use L'Hopital's rule. So I'm going to go ahead and do it for number 5 above, because you can actually do it for all the problems that we did up at the top. So number 5, we did it by direct substitution, and we ended up with 6. Now, I'm going to show you how to do this another way using L'Hopital's rule. Again, if I go ahead and do the limit of the top and the bottom separately, this is the first thing you need to show, that you do end up with either 0 over 0 or infinity over infinity. So I do have each piece being 0. So I have 0 over 0. L'Hopital's rule says then you can do this. You can take the derivative of the top separately, which is 2x, the derivative of the bottom separately in this case, which is 1, and then go ahead and take that limit. So if I take this limit by doing a direct substitution, I get 6. And that will give you that correct answer. So this problem, number 5, We could do by factoring, which is actually quicker, or we can use this idea of L'Hopital's rule. Okay, these problems on the bottom here now, these you will have to use L'Hopital's rule. So first thing you always want to check is that can you use L'Hopital's rule? So that means you are going to check the top and the bottom separately, and this is the work that you need to show. So if I plug in 0, cosine of 0 is 1, 1 plus 0 minus 1, this gives me 0 on the top, and then I know the bottom is going to be 0 pretty easily, but this is the work that you need to show. So I do have 0 over 0. So L'Hopital's rule says that I can go ahead and take the derivative of the top separately, which is negative sine of x plus 2, do the derivative of the bottom, which is 3, and then now go ahead and try to take the limit by doing a direct substitution. So now if I plug in 0, I end up with 2/3, and this is this limit right here. Try the next one. Same thing. So let's check that we can use L'Hopital's rule. So if I plug in 0 here, e to the 0 is 1. Right, so I have 1 plus 1 minus 2, so this is 0. And let's check the bottom. So cosine of 0 is 1, so 1 minus 1 is also 0. So I can use L'Hopital's rule. So again, we're not doing the quotient rule, you just do the derivative of the top and the bottom just separately. So the derivative of the top is e to the x minus e to the negative x. Derivative of the bottom is 2 sine of 2x. Now, I'm just going to do this in my head. If I try to plug in 0 again, you'll end up with 0 on the top again and a 0 on the bottom again. So we can actually use L'Hopital's rule again. So I'm going to do L'Hopital's rule one more time. So the derivative of the top is e to the x plus e to the negative x. The derivative of the bottom is 4 cosine of 2x. Now let's plug in the 0. Notice you get 1 plus 1 on the top. Cosine of 0 is 1. So this limit is 1/2. So you can do L'Hopital's repeatedly as many times as you need to if you get 0 over 0 or infinity over infinity. But if you're doing this more than 2 times, something's probably not right. Okay, let's finish off the last 2. So same thing happens. You will end up with 0 over 0 here. So I'm going to do L'Hopital's rule. Oops. So the derivative of the top is cosine of x. Derivative of the bottom is 2. Now if I plug in the 0, I do get to a limit of 1/2. And then here, notice, let's talk about this piece here. This is saying the limit of the tangent of x as you approach pi halves from the right-hand side, from the left-hand side. So the thing you need to remember is you do need to think about the graph of the tangent. So remember, this is your tangent graph. We are approaching pi halves from the left-hand side. So as this graph goes to pi halves, remember the tangent graph goes to infinity. So this limit is infinity. And then if you take the limit of the bottom piece, the secant graph, you're also approaching infinity. So this one, you're going to end up with infinity over infinity if you do a direct substitution. So that is another indeterminate form. So we're going to do L'Hopital's rule, which says, let's take the derivative of the top. The derivative of tangent is secant squared. So I've got 4 secant squared. And then the derivative of the secant on the bottom is secant tangent. And before I go ahead and plug in the pi halves here and take the limit, I'm going to clean this up a little bit. Notice one of the secants will drop out. So you end up with secant divided by tangent. And if you simplify that, changing things to sines and cosines, you're going to end up with just the sine on the bottom. So typically with the trig functions, you want to try to clean it up as much as you can. And now if I plug in pi halves, the sine of pi halves is 1. So this limit is 4. Okay. Last thing I want to show you is this one. If you just try to use L'Hopital's rule here, this is what happens. The derivative of the top is e to the x minus e to the negative x. The bottom is 2. And if you plug in 0, you get 1 minus 1, which is 0 divided by 2, which gives you 0, right? 0 divided by 2 is 0. It's if you have 0 over 0, that's indeterminate. So this is what you would get if you use L'Hopital's rule. But this actually is the incorrect limit. This limit, actually, the correct answer is infinity. If you look at this graph, you'd notice that this graph goes up forever. So the thing to be careful about is make sure you have either 0 over 0 or infinity over infinity before you start using L'Hopital's rule.